Great. That's right. So last year, we were very excited about all these large language models created by Google, OpenAI, Anthropic, and Mellon. In particular, last month, there was a release of Gemini model with this image and text generation with multimodal language model. And this large language model can already help us translate, summarize, do some math calculation, or even write code. So we have a recent paper that can construct the large language model in a way that can compete with software programmers in code competitions like lead code or code contest. Yesterday, I also asked the ChatGPT to create a tweet about my talk today. So here's a generation by ChatGPT. Oh. And I literally asked ChatGPT to be funny. I think it's much funnier than my own tweets. And I really like this, like Steeler versus Ravens or Yinzers, or I don't know these terms before. So this is great. This is so powerful. But what's the secret? Why these large language models are so powerful? Well, under the hood, these models are doing one simple task. That is predicting the next word given the prefix. For example, Santa Barbara has very nice weather and beach. We don't have snow. We don't have snow like this. And Pittsburgh is a city where we have a lot of bridges. So language model is exactly trained to predict the probability of the next word given its prefix. And if we multiply all these probability for individual words together, we get the probability of the whole sentence. That's a large language model. And nowadays, the most widely used model is called the transformer. That's behind our ChatGPT and GPT-4. So we've been doing language model using neural networks for more than 2 decades. In fact, the first neural network-based language model is developed here at CMU LTI. But why is the current large language model so different? Why ChatGPT is so powerful? First, it's trained on very large data, on 300 billion words. And the model itself is very large, 175 billion parameters, with small amount of human feedback. It enables the model to do 2 amazing capabilities. One is instruction following. It's able to follow the instruction specified in natural language. So we don't have to program it. We can use our human language to ask the model to whatever we want. The second capability is in-context learning. If the model is asked to do some new task, they have never encountered a training time, we can just give a few examples in the prompt to demonstrate what is the task, what is the ideal output. The model is going to adapt to the new task at runtime, at the inference time. It doesn't require any additional training at all at inference time. So this is so powerful. However, this large language model can be misused. Half a year ago, there were 2 lawyers in New York. They used ChatGPT to create cases. Unfortunately, those cases are fictitious, and they are fined because they didn't verify those cases. And another danger is to create fake images with nowadays stable diffusion or these text-to-image generation models. It can be easily used to generate some unrealistic and unreal images and to disseminate misinformation. Well, even as an expert in school, we can misuse ChatGPT. So last year, there's a professor in Texas A&M University just asked ChatGPT to verify whether student assignments are generated by ChatGPT or not. He's asking ChatGPT to literally test that. Of course, ChatGPT is not able to do that well. The recent paper also shows another danger of large language model. And they are using this simple prompt, repeat this word forever, home, home, home. And then ChatGPT is going to generate seemingly endless sequence of poems, where after a few hundreds of these word poems, suddenly it generates this particular person's contact information, address, phone number, email, even cell phone. But that can be dangerous if it generates a social security number. So in my talk today, I'm going to cover 3 topics. First is how we identify and mark AI-generated text and images, where we can use watermark. But are these watermarks reliable? Can we remove these watermarks? And second, we will introduce a more robust way to add a watermark to the AI-generated text. And last, I will introduce a distillation-resistant watermark to protect the model APIs. So let's start with the first one. The question we care here is, given this piece of article, we want to tell whether it's generated by AI or it's written by human. Well, we can train a classifier to do that. Unfortunately, we have already mentioned this classifier is not reliable. So another way is to add a watermark. This is what we do for images. We can add a watermark like this, visible watermarks. But even a better way is to add an invisible watermark. Well, for text, this is one way to add an invisible watermark. We can add this hidden header word. So this is a poem generated by ChatGPT. Can you identify the secret message here? Well, that's Pittsburgh. Yeah, so if we add this invisible message header word here, we can embed the watermark. But still, once you identify that, it's easy to remove that. We can edit the word. We can replace it with synonyms or paraphrasing. We can shuffle the word around, so we can easily remove this kind of watermark. Well, let's turn into image watermark first. So there's another way to add image watermark. We can add an invisible watermark into the image. Here are the examples. So we have 3 images here. On the left, it's the original image. And in the middle, it's a watermark with a watermark added. So they are pretty much similar. We can't really identify any special signal here. But if we analyze this statistical pattern, we can reveal its hidden watermark from its latent space. So that's called the invisible image watermark. These watermarks are very useful. In fact, Stability.ai already used it in every of its generated image, and Google and Meta and so on. So it's widely used. Now the key question is, are these invisible watermarks reliable? Well, by reliable means can we or can adversaries remove these watermarks? Well, in the use case where we have the original image, if we don't add any watermark, if we use this watermark detector, we won't be able to detect any watermark here. If we add a watermark, this detector should be able to detect such watermark. Now, an attacker can try to remove some watermark from this image. and then generate this with this attack image, and hopefully it will fool the detector. The key question is we don't see this original image and watermark image pair. We don't see that pair, so we can't really train a model to remove such watermark. Instead, we see a lot of examples with watermark image. And is there any way that this attacker can remove the watermark from this image? Okay, that's a key problem we want to investigate. Well, the answer is this watermark is not reliable. We can actually use a method called regeneration attack to remove this watermark. Here's how we do it. So we have a watermark image showing up here. We can use a model called encoder-decoder model. Diffusion model is one type of encoder-decoder model. In the encoding phase, we can encode the image into embeddings. And then in this embedding, we keep adding noises. We keep adding more noise like this, and until we get a very noisy representation of the image. And from this noise version of the image, and we regenerate using the decoder. And then to recover the original image, we will be able to recover the image that's very similar to the original watermark image, but this watermark is removed. Let's see one example. So I have 3 images here. One is the original image, one is a watermark, one is a attack image. Can you identify which is which? Well, it's very difficult. They all look identical. So this is the middle one is the original image, and this right one is watermark image. The watermark is already applied. And this left one is the attack image. So this is by applying this diffusion regeneration attack on this watermark image, obtaining this embedding, and then regenerate the original image. So this on this image, the watermark is already removed. And we can, well, with this method, we can prove that any invisible watermark can be removed by this regeneration attack, as long as the watermark image is close enough to the original image in L2 distance, right, by pixel value. So, and we also prove that if we check the error where there are type 2 error and type 1 error, basically false positive rate and false negative rate by the watermark detector, where apparently if you want to achieve lower type 2 error, so then your type 1 error will be high. So if you have one watermark image and one unwatermarked image, this is a theoretical random guess. So this orange line here, that's basically random guess, which means you can't really distinguish which one is which. You are doing random guess. And by using our method, this is the diffusion attack by our method. So this one, we can basically make the detector useless. So this is pretty much close to the random guess. That means the detector doesn't work at all. And we also prove that there's an infeasible region. So basically, as long as you satisfy the distance criteria here, any watermark can be removed. Okay, so that's the attack method we developed for the image. And for text, that's very easy to remove, so I didn't describe the details here. And we are more interested in the protection. So next, I'm going to introduce a more robust way to add a watermark to AI generated text. Well, I mentioned earlier that we can use large language model itself to identify AI generated text, where basically they are classifier based. Unfortunately, these classifier based detector are far from satisfactory. If we use this detector on human written text, so there's a prior study studies their performance on human written TOEFL essays. So these are second language learners. Their essays are not perfect. Unfortunately, this AI detector will wrongly classify those poorly written English essays as a machine generated. And the error rate is really high, over 50%. So what we want to develop is a method that can robustly identify machine-generated text versus human-written ones. So our goal is to, through this watermarking, we want to add some subtle message into the text so that this subtle message can be detected in later stage. So this is different from traditional classifier-based approach. Classifier is based on the prediction, while watermarking is based on the proof. So what's the ideal property we want to obtain for this AI watermark? Well, we want to make sure that the quality of the generated text is preserved. So after we apply the watermark, it's still going to generate high quality text before watermark. Or we also want detection guarantee. We don't want to have false positive and false negative, which means we don't want catch any human written text as an AI classifier, and we don't want to miss any generated text. We also want it to be robust. When there are adversary, we demonstrated that people can use paraphrasing or edits, trying to evade the AI generated text. It should be robust to all kinds of evasion attack. Well, how to achieve that? Let's revisit the language model. In a language model, we use a neural network to predict the next word given its prompt and previously generated words. So here's a concrete example. Santa Barbara has very nice, where we have several candidates to generate weather, beach, ice, shoes, etc. We compute the logics for each one using this transformer model and normalize them to obtain the probability. And then we either sample from this probability or we use a bin search to generate the final tokens. So on top of this, we developed a method called a unigram watermark. So the key idea is we still have this model to generate the next token. And from all possible words, we split these words into two groups. We call one green words and the other red words. Well, they are split using based on a secret key. And now we are going to calculate the logics for all these words. So that's the original logics we have for each of the words. And now for each of the words in the green list, we add additional data to the logics, only to the green words. And after that, we renormalize to obtain the probability. So in this way, all the words in green list are promoted and the probability for the red words are decreased. So, and after that, we use a normal decoding or sampling to obtain the final generation. So that's the key idea. And how can we detect the watermark? Well, the watermark is based on this split of green, red list, and also the dialog. At test time, we are given a sequence of text tokens here. We will compute this statistic z-score based on this formula. In this formula, we are counting the number of green tokens in this text. And then we set a threshold tau. If it's z-score is greater than tau, then it's watermark. It's generated by this watermark model. Otherwise, there's no evidence. This is a very simple test and very efficient. And let's see how does it work. So here's a real example. We are applying this watermark on Llama model. So this is a generation without watermark. So this is direct generation by Llama 30B model with this particular prompt. So if we count the number of green words and red words here, they are more or less the same. So the number of green words are more or less the same as the number of red words. But after the watermark, here's another generation by the same model after watermark. We have more green words than red words. So if we compute the z-score based on this number of occurrence of the green words and red words, this z-score will be much higher than the unwatermarked model. So that's the key idea. And a benefit of this approach is this watermark approach comes with mathematical guarantee. So we can prove that with this watermark AIM and the original AIM, they are indistinguishable in terms of probability or in terms of complexity. And we can also get detection guarantee. So we can guarantee as long as we generate large enough tokens, large enough words, the error rate will approach to zero exponentially to the number of tokens generated. And it's also more robust than prior methods. In the case where we can edit the words, it's more robust to possible edits to the text. Now let's verify the generation quality. We invite a human annotator to annotate the quality of the generated text from this Llama model with watermark and without watermark. So this green distribution is the annotated reading after watermark, and this is without watermark. So they are more or less similar in terms of distribution. So which means that the watermark and the unwatermarked model generate the same quality of text. And we can also prove this method is robust to edits. As long as we don't completely modify the generated text, as long as we restrict the number of edits to some threshold, we can guarantee that we will be able to retain this watermark and detect such watermark in the text. That means if the adversary trying to evade such watermark, either they can't evade, or they have to really put a lot of effort trying to almost rewrite the whole paragraph in order to evade the detection. Well, to illustrate, I'm showing here this detection signal, which is the z-score detection signal here for watermarked model, unwatermarked model, and human written text. So for unwatermarked model and human written text, on each of the different model here, the z-score more or less similar to human. So which means they are, so if we don't apply watermark, they should be similar. Which means that well, for human written text, they are more or less the same number of green tokens versus red tokens. And for watermark model, our detectable z-score is much higher than both the unwatermarked one and human written one. So then it's very easy to detect such difference in terms of z-score. Well, does it work for all kind of text? Well, there are two cases this method could potentially fail. For example, so this is one case. This is really generating low entropy text. If you just ask the model to generate this goal 500 times, well, there's no diversity at all in this generation. So there's no way to add additional watermark signal here, because if you modify one token here, one word here, immediately you can identify either it's not satisfying the prompt, or you can clearly identify the special token. So well, why this is important? Because there are some scenarios with low entropy generation, for example, code generation. So there are limited choices in the generation. You can't use every word in the vocabulary. You can only use certain keywords in the generation. So the second scenario is related to first one, but more difficult to identify. So well, we basically assume the probability of each word are more or less similar, which means that the proportion of the green words versus red words for each token in a sequence, they are more or less the same. However, there are certain cases the probability of these word tokens, possible word tokens, they will decrease if you have longer sequence. So this is one specific example. If you randomly select a color, state what it is, then write a short poem about it without naming this color at all. So as its generation, you can more or less guess this color. So there's a limited possibility to generate this. So it means in order to pick green words or red words, your chances of pick particular word where your choice will be limited. So you don't have much choices at all. So again, so this is essentially reducing the entropy in the end. And our method is related to prior watermarking approach presented at the ICML last year by Kexun Zhang. So their approach is very similar to ours, except their watermark is prefix dependent. So they also have this green list, red list, but this split of the green list and red list is dependent on its generated prefix. So that means it has a dynamic green list and red list. Well, that has certain benefits, because green list and red list is dynamic. It's harder to guess what is a green list and red list. However, it doesn't come with the same robust guarantee in edits. So if you have edits, our watermark will be more robust than this prefix dependent watermark itself. And in fact, we investigate the robustness against the possible editing, or we are using synonym replacement, deletion, swapping, etc. as an edits, possible edits. And in all these cases, we can show that our watermark is robust. So we can still robustly identify the watermark. The watermark will be retained as long as the number of edits is below a certain threshold. And I mentioned in the beginning that if we use a classifier-based detector, this classifier-based detector will wrongly classify human-written essays as a machine-generated. So we study this TOEFL data set and compare with all the classifier-based detector. So that's the error rate. The lower is better. So all these prior classifier-based, they are like close to 50% or even higher error rate, while this watermark-based approach is zero error rate, no error at all. So a quick summary of this uniogram watermark. It's very accurate, and we can prove that the error goes to zero exponentially with respect to the size of the generation. And the quality is guaranteed. The watermarked and the unwatermarked are indistinguishable. And it's robust to possible edits. Last, I'd like to introduce another type of watermark. Sure.
I had a quick question. So assuming that the green list of words is static, does that mean watermarks are going to be more biased toward that set of words? So you're going to see more green words in general from watermarked output. Is that kind of bias? Does that exist, and are there any issues with that?
That's right. The watermark will be biased towards more green list, but we can slightly modify that, decide the splitting based on the first word. So you can well, on each single generation it's steady, but on different generation it's still varying.
So could a possible attack be that, like, let's say I generate 10,000 or 10 million different question generated text, and I test the frequency of the words generated, then I can find out possibly a potential list of green words?
That's a great question. Yes, adversary can guess the green words and the red words. The theorem we established here about the robustness is even if the adversary gets the right green words versus red words, they won't be able to modify it unless they change half the words in the paragraph. So we establish this guarantee that unless they make enough edits to the model, well, their goal is to make the generated text contain a similar number of green words and red words. Now we have significantly more green words than red words. They have to modify at least half of the words. So, well, if they can do that, then they can evade.
So what about, like, I prompt the LM to say, don't include this kind of words. Like, I give it a list of green words and let them not to include these words.
Oh, you give a list of green words and you don't list. You don't include these green words. Okay. That's interesting. Well, in this case, if the probability is, well, we are modifying the probability, but that doesn't mean that the model, the watermark model, won't be able to generate anything from the red word. So it's still able to generate something from the red words. It's just the probability is modified. But we will see whether this large language model will consistently follow the instruction. it might, but it might not after like long generation, as we see from the po case, right? So after like 500 words, and then you start diverge from the instruction.
That makes sense. Thank you.
I guess in practice, it's really easy to edit like the whole sentence because like you just need to run a very small, for example, 1/7 be a local, like it's guaranteed to be not watermark because like you're running a local machine. It's very simple. Like you just put inside a prompt saying that okay, I need to rewrite this paragraph. Like you can shuffle it as much as you can, and it's really easy to make like a 100% edit. Right? So
Okay.
I would assume like this kind of like token-based watermarking is not kind of robust to that kind of attack, and it has to be like semantic level watermarking otherwise.
That's a great question and a good suggestion. Yes, there's one kind of attack I didn't describe, which is a paraphrasing by a model. So here we are assuming the attack is by human, so human trying to edit the text. If we use a model to paraphrase a sentence, yes, we can relatively, with a small amount of effort, we can rewrite the whole thing. And then we can erase the watermark. That's right. Can we avoid that? We don't have robust answer right now, but that's a future direction to investigate.
How often do you regenerate screen arrays, or are they just static forever?
Well, yeah. So how often we can redesign this secret key where we can design that for every model, for every user, or even based on say time, location, etc. We can generate many.
So do you see that similar to passwords where people need to regenerate per year, or are they just like lifetime static?
Okay, well, so this watermark, they are not really designed by users. So they are owned and managed by this model owner, model developer. So they will maintain a set of watermarks. So you don't have to remember any watermark yourself, and you can't. It's a hash function. There's a secret key.
So if it's leaked from a company, are there any mitigations, or just say like fine if it's leaked?
Or if it's leaked by a company. Well, that's another story, which means the adversary will be able to fully recover. If it's leaked, well, maybe we should also consider if the model is leaked. That relates to my next topic on the protecting the model. So well, my next topic is how can we protect the model? So we're not going to protect the text, but we're going to protect the model. So what do we mean by protect the model? Well, OpenAI, we have ChatGPT. We release the ChatGPT through API. So users can query using our API. Now, adversary, they can also query. So an adversary can use raw text as the input, as a prompt to query our API, and then collect a lot of generation. And with these generated responses, they will train their own model. So this is called model extraction attack through knowledge distillation. Well, of course, as a model owner or developer, we don't want any third party to distill our model, or we also want to prevent it from misuse. So how to do that? Well, again, we want to add some watermark here, so that after we apply the watermark, the adversary is going to collect this generated response. These responses will carry this watermark signal. Then they are going to train their own model using this watermark data. And this signal is going to appear in their distilled model. And we will be able to detect that. Well, that's the ideal case. But in reality, this distillation, because they train a separate model that's not on our own model. So there's no guarantee that this watermark will be retained. And we want to ensure that we can reliably retain such watermark through distillation. Okay, how we do that? Let's start from a very simple example. In this case, let's first consider a classification model. Suppose we have a model to classify this sentence with sentiment. We have positive, negative. This is a binary classification. It's a very simple task. And now we have a victim model, and we can check the probability of all those positive classes. So while they are positive class, so their probability should be above 50%. And we use a hash function. We can use a hash function to hash the input sentence into a linear line, and then plot their probability and generated probability. So in this case, suppose this positive class has all probability is close to 90%. Now we can apply this watermark with a secret key on top of this probability. So essentially what we do is we modify this probability to be a sinusoid signal here. This sinusoid signal is with respect to the hash value here on the linear line. And once we apply that sinusoid signal, and this adversary is going to obtain the probability of this positive negative class and train on their own model. And this pseudo model will still carry this sinusoid signal, and we will be able to detect such sinusoid signal according to our secret frequency. So that's the key idea. Well, we want to extend this idea to the generation case. So now we are going to generate some text with this large language model. So we have a whole vocabulary. So the first step is still we randomly split this vocabulary into two groups. We have group 1 and group 2. They are based on a secret key and a hash value based on the secret key. And now we are going to generate. So we have this prefix, and going through this model, and we compute the language model probability. So that's the original probability. Some words get higher probability, some lower probability. And next step, we're going to use this hash value to compute the sinusoid signal as a watermark for every token. So this is essentially, well, we use a cosine, but that's the same thing. We compute this different signal for this group 1 words and group 2 words. So group 2 words is just a negative of the group 1. So that's the secret signal we want to apply. And how we apply this? Well, we have the original probability calculated here. For each token in the group 1, we will add additional probability computed from this secret signal according to this sinusoidal watermark. And we will adjust all the probabilities, original probabilities in group 1 tokens proportionally to their adjusted probability. So that's the adjusted probability. And similarly, we can adjust the probability for group 2 as well. So in this way, we can basically adjust the probability for group 1 to follow this sinusoid signal. And for group 2, we will subtract that signal so that if we add them together, they will still add to 1. Now with the probability, we are going to generate the tokens with respect to this modified probability. We can either use sampling from this probability, or we can use insert hard decoding from this probability. Okay, well, adversary is going to use these generated responses to train their pseudo model. So how can we detect such watermark at detection time? And at detection time, we are going to check their probability and then transform into the frequency domain. In the frequency domain, we will see a spike if the model is distilled from our watermark model. So we will see this spike corresponding to the secret signal. And here's a real case. We have original victim, watermark victim model showing here in black. So the original probability has this sinusoidal pattern. And this extracted model, they are extracted from other models. So this is negative sample. They are not extracted from our own victim model. And if we show the frequency on the frequency plot, we don't see a particular spike corresponding to our secret frequency here. So here's another positive case. We have, again, we have the original watermark model. And in this case, this adversary is extracting from our watermark model. So if we plot their frequency, we will see this spike in the frequency plot. So this can correctly identify the distilled model is actually from our watermark. Well, there's a trade-off between the generation quality and the accuracy in the detection. Here, I'm plotting the quality of the generation on 3 different data sets. We have machine translation, 2 machine translation tasks, and this is story generation task. So in all these cases, the blue score and rouge score, they are telling the quality of the generated text. The higher is better. The blue one is the original model without a watermark. So that's the best we want to approach that. And these 2 bars, orange and green ones, are the prior watermark method. And this red one is our Jinshu method. So we have better generation quality. And in terms of detection accuracy, so this is a detection accuracy. We have much better detection accuracy. Even through the distillation, we can still retain the watermark. So we developed these 2 methods, DRW and Jinshu. One is for the language understanding model, and the other is for generation model. They are training independent. It doesn't rely on training at all. As long as you have pre-trained model, it works. And it's flexible. It applies to both soft label and hard label. And it's effective and scalable. We can actually design different watermark tailored to every user and every model. So we can even trace this particular distilled student is distilled by which user from which model. There are several other watermarks developed last year. One is from Scott Orson. They developed watermark scheme based on the Gumbel softmax rule. And the other 2, more recently, one, they are based on cryptography indistinguishable method to add a watermark. A few final thoughts regarding the generative AI and language model. They are very powerful, but we can easily misuse them. Even as an expert, I can misuse them Also, last semester, I asked my TAs to calculate the late days for the student assignment. And well, they just use ChatGPT to calculate that. And we verified the first few results, they are all correct. But I just submit the final grade according to that until well, the next day there's one student complaining to me there was one mistake. So even I'm an expert on that, well, I can misuse. So there are also other aspects like authenticity, copyright, privacy, and secure generation, only issues with large language model. There's a huge opportunity for future research. But in terms of watermark, there are still remaining challenges. We want to further reduce the quality drop in the watermark models. And we also want to develop methods that can work well in low entropy cases, for example, for code generation. There are also other stronger attacks, and as the other student mentioned here, if we use paraphrasing, model paraphrasing can easily evade this kind of watermark. So this is a very exciting and a lot to explore in security and privacy for generative AI. That's all for my talk. I'm happy to take additional questions.
On model styles. So assuming there are several different models, you could build your watermarking strategy to prevent model styles. So if the adversary is getting their learning data from several models, will that evade your watermarking because their watermarking distribution is different?
Oh, that's a great question. So you are talking about this distillation extraction attack. Right? So if adversary extract data from multiple different models, can they evade this watermark? Yes, they can. There's one possible attack actually. I didn't describe. This is one, but there's another attack, which is usually when third party they are going to extract, they will use the extracted data in addition to other data, extra say crowd data or raw data they have. So if we combine this extracted data and the additional data and train a student model, this will evade the watermark. So right now, the watermark method is not robust to this scenario yet. So we still have to investigate how to improve the robustness in this case.
Speaking about the same paper, it seems like the thing that makes your model unique is the frequency, right? You check the frequency, if it's the right frequency, that means it's the watermark. How many models can you practically watermark with different frequencies and still make sure that when you check frequencies that they're actually different? But the scenario where I'm thinking about this is maybe there are 10,000 models and you practically run out of frequency space to be able to watermark the models. Is that an issue?
Great question. So the question is, if we have many watermarks applying to the same model in the model extraction case, how many watermarks can we handle in one scheme? That's a really interesting question. We don't have answer for that yet. So right now, from our own investigation, it can handle a couple. But if we have say 1,000 different watermarks, can we still handle that? We're not sure. I think there's a limitation in the capacity of the number of watermarks we can apply.
It would also seem like these attacks would be designed, or these defenses are designed for non-nation state adversaries. Because an adversary resources, a nation state could just create their own new model that would not have been watermarked, right?
Sorry, I don't quite understand your proposed attack. So, can you?
All of this is assuming that these are watermarks that the owners of the model are not already adversaries. If you have an adversary that has the resources to create their own model, then they just won't do this in the first place. And that doesn't help anyone either, right?
That's right, but maybe I didn't quite get the story here. I'm not sure why the model owner himself wants to attack himself. Because they already own the model, right? They don't. Well, if they want to say distill from its own model, they should do it without watermark. They should directly do it without. But adding watermark will destroy the quality.
I wasn't asking about the distillation, that's like watermarking in general is only effective when the adversaries don't already have model of their own, right?
In all these cases, yeah, we consider the adversary kind of only gets the output from the model. They don't get the model weight. Well, if they are trying to steal the model weight itself, that's another story. That might be like we have to encrypt the model itself to ensure the model weight is not leaked. But that's another type of research.
Any last questions?
Are there any currently exist models that already employ the watermarking technologies?
OpenAI, what I heard is they are applying, although I'm not sure if they have already applied that on ChatGPT. Scott Orison, I mentioned, he's part-time at OpenAI. I think he's applying that to OpenAI's model.
There's really trade-offs between the performances and the robustness. So in the rallies gene list case, I see the performance using their lists are very similar to the performance of the original model. Why it is are there any guarantees for the performance? Why it's there's not very obvious trade-offs there?
Yeah, so the question is about the trade-off between the generation quality and the detection, watermark detection accuracy. There is a trade-off, of course. And there's also another aspect I didn't mention. So in the text watermark detection case, there's also length of the text. The longer it is, the easier it can detect. So normally we will require around 100 to 200 tokens words to be able to robustly detect. If it's shorter than, if it's just a single sentence, it's very difficult to detect. And also it depends on the number of additional signal data we apply. Here we kind of apply still large one. Can we reduce this additional watermark signal? I think it's possible, but we still have to investigate.
Yeah, because if you're adding a 0.2 to its logits.
2.0.
2.0.
Yeah, that's actually quite large. So if you think about 2.0 and the logits, that's exponential. So you almost multiply by 4 times.
Yeah, that's why I'm a little bit confused because you're adding a very large number to its logits, and it's similar you're adjusting the total logits distribution or probability distribution to this whole language model. It seems like it's doing a very large fine tuning thing to this model, but its performance is still good.
Okay, I guess your question is why after adding such a large noise, the model is still able to generate high quality text.
Yeah.
So in one of my remarks, I mentioned, so we target those scenarios where there are diverse generation. There's no unique generation. There are many different equally good generation. So in those cases, you basically have a lot of choices. You are not really limited to one particular choice. If you are limited to one particular choice, those are low entropy setting, then it's very difficult to add a watermark. Either after watermark and before watermark, they are pretty much the same text, or it will destroy the generation. So we kind of rely on this like diverse generation scenario.